We know that functions are relations where the inputs and outputs are connected such that each input maps to exactly one output. Whenever we're working with such functions, there's some language and notation that we use that is called function notation that really helps us to organize and make some interpretations about the functions with which we are working. So to exemplify this, I want to use this example right here, this relation between x and y, defined by y equals negative 5x plus 2. Now, this relation actually does turn out to be a function, and you can kind of see why that is, because if I just make a little table of values to show this relationship here, so I'll treat the x's as the input. So if I pick just any random input, say the number -1 for x, you're only going to get one output for y, right? Because when you plug it in and then you solve for y, you end up getting a 7 for a corresponding y value. So the same is going to be true no matter what input you plug in. You're always going to get just one unique output for each particular input. So I'll just give a few examples right there. This can be further exemplified too if you make a graph of this, because if this is your x-axis here and your y-axis here, and I plot all of these different coordinates, so -1, 7, and 0, 2, 1, -3, and 2, -8. That gives you a little flavor of some of the ordered pairs here, and you can, of course, plug in decimals. So, for example, if you plugged in 0.5, you actually get -0.5 as an output, so you'd have an additional point right here, and you could plug in a bunch more decimal x coordinate pairs, and it turns out that your relation actually just ends up being an entire continuous diagonal line like that, and it passes the vertical line test, so we definitely know it's a function. So where the function notation is really going to come into play right here is really just kind of replacing the output variable. So what I mean by this is that instead of defining the relation with a y as your output variable, what function notation will do is we will have something similar to what I will write right now. We will have something like f of x equals -5x plus 2. So there's quite a few things that we want to be able to process about what I just wrote right there. So I'll bullet point each of these kind of ideas. So first of all right here, I want to specify that f of x right there, it just replaced y, or just in general, whatever the output variable was, if the output variable wasn't y. The second thing, which you've heard me say at least a couple times by now, is that we read it as f of x. F of x, whenever you see such a thing. So what f actually is f is actually the name of the function rule that maps each of your inputs to the outputs. And a common misconception that we want to clear out of the way here as well is it does not mean f times x. That's an important thing to recognize, because when you see that, you think, oh, that looks like multiplication, because they're right next to each other. At least there's the parentheses with nothing between. But we're not talking about multiplication at all right here. So really, just the thing that goes in the parentheses is really your input. So I could also say f of c, okay, and then now c is my input. No longer is x my input, so my rule would have to change to -5 times c plus 2, and then f is just denoting the name of the function rule. So I think you can get a better grasp of kind of what's going on with this f name if I put this into a mapping diagram form. So in a mapping diagram, you have two different sets, and the first set here will be our domain, and the second set will be the range. And so we can usually think of these as being like the x's, and then we're going to map them to the y values over there. It's just that if it happens to be a function, the rule that defines this relation or this function gets called a name, which I happen to pick f. We could use lowercase letters, sometimes we'll use capital letters. In this case I used a lowercase f. And when it maps to an output, we no longer really call it y, we'll call it f of x. And f of x is just going to be the same answer you would get as your y value, it's just we call it f of x. So if you were to actually plug in, let's say, n as an input, then n is going to map to f of n, whatever the corresponding y value would be. So if I actually like pick a number, so let's say if I picked 1, then 1 is going to map to f of 1. But if we were using the rule f that we kind of defined right there, the rule negative 5x plus 2, we actually should know and be able to figure out where this input of 1 is actually going to map to. And we actually have that reflected right there in the table, that the 1, when it's an x value, actually maps to a negative 3y value. So I could actually, instead of writing f of 1, if I wanted to, I could put negative 3 right there. And the reason why we know that is because f of 1 does equal negative 3. So you can see that really in the parentheses right there, you're just specifying what the input is. And this right here is actually the corresponding output for that particular input when we did this particular rule that has the name of f. So getting a little bit more in depth with some of this, we're going to do a little bit of interpretation of function notation and a little bit of a context right here. So what it says in this couple sentences at the top right there is it says to let f of t be the outside temperature in degrees Fahrenheit t hours after 6 a.m. And then explain the meaning of each of the following statements, in which I have 3 examples here, of course. So I put some colors there on purpose because what we really have here is we have a relationship between the green variable and the red variable. Now the green variable is really corresponding to f of t, and the red variable is corresponding to t. So in general, we kind of have a mapping that's mapping from t to f of t going on right here. So what that means then is that this right here, this 0, is kind of like your t. And because t is really about the number of hours after 6 a.m., and here we see a 0, that really is referring to the fact that we are 0 hours after 6 a.m., which of course means it's exactly 6 a.m. if it's 0 hours after that. And when we apply f, this rule, to this, it's going to give us the outside temperature. Because we have an equal sign and it equals the number 58, then we actually know that this right here is actually the temperature in degrees Fahrenheit at that particular time. So really we can interpret this statement to say that 0 hours after 6 a.m., it is 58 degrees Fahrenheit outside from that particular statement. So right next door to this, we have this f of 6 equals k. It's pretty much almost an identical statement, so we just have to recognize that right here 6 is the input, and the input variable is the number of hours after 6 a.m. So we have to treat that as being 6 hours after 6 a.m. If you work that out, it ends up being noon that particular day then. And it's equal to k, and that's going to correspond to your output in degrees Fahrenheit. Now, k is not actually a number. It's like we don't know the number of it, right? But it's still going to be k degrees Fahrenheit. So the way we can interpret this statement is we can say that 6 hours after 6 a.m., so you could say just at noon would be fine, it is k degrees Fahrenheit outside based on that statement. And then finally, one last statement to interpret right here. You can see there's an inequality symbol of a less than, and on the left-hand side of that, you can see that we've got f of 3, and on the right side of that, we've got f of 9. Now, we don't actually know what f of 3 gets sent to in terms of an output, right? Like f of 3 equals, we have no idea. And same thing about f of 9, we have no idea. So what the 3 means and what the 9 means is because they're the inputs, they're the number of hours after 6 a.m. So we do know the times we're working with. So it does turn out that the 3 is really going to correspond to 9 a.m. because that's 3 hours after 6 a.m. And then if you work out what 9 hours after 6 a.m. is, it ends up being 3 p.m. So we do know the corresponding times that are the inputs, but we don't actually know the temperature that f of 3 is. We don't know the actual temperature that f of 9 is, but at least we do know that when we compare the temperatures, that the F of 3 temperature is less than the F of 9 temperature. So really kind of putting this all into conclusion, we can say really that the temperature outside at 9 a.m. is less than the temperature outside at 3 p.m.